Hi there, Andy Warwick here. In this video and the next, I'm going to be taking a cultural historical look at the origins of the first fully mathematical field theory, electromagnetism. And I'll be focusing on three sites: Copenhagen, Cambridge and London. And a broad question to keep in mind through these videos is why during the 19th century Western Europe was such an extraordinarily innovative site for physics. I'm going to be asking how new phenomena were produced and why they were so hard to detect and interpret. First philosophically, then heuristically, and finally mathematically. We'll see this is a good example of an area which was first dominated by experiment and non-mathematical reasoning. And then we'll look at how electromagnetism was not only mathematized, but turned into a completely new kind of theory, what came to be called field theory. So until around 1800, electromagnetism didn't just not exist, it was predicted by the greatest theorists that it couldn't exist. And I'm thinking here of Pierre-Simon Laplace and his school in Paris. They believed that because their model of mathematical theorizing was Isaac Newton's inverse square law of gravitation. Laplace had applied that to electro and magnetostatics by viewing them as weightless fluids made of microparticles that attracted or repel according to quantity and distance. So on this slide we can see Charles Coulomb's famous balance of 1785, in which he tried to make a plausible argument that electrostatic forces acted according to an inverse square law like gravitation. So here you can see two little pith balls which can be charged so that they move apart by repulsion, and then you can use this little knob on top to force them back together. And by the torsion you're applying, you can make a plausible argument that this is acting according to an inverse square law. Now, there are two important things to remember here. The first is that the force between these spheres is linear. It acts directly between them. And secondly, that Laplace thought electric and magnetic forces were entirely independent of one another. But in 1800, Alessandro Volta, professor of natural philosophy in Pavia, announced a new discovery, the voltaic pile, what we'd call a battery, the first source of a continuous electric current. So here's Volta demonstrating his new battery, the pile, to the Emperor Napoleon, and you get the idea this was a really big deal. The pile could make new chemistry happen. It could split water into hydrogen and oxygen. It could produce new elements like sodium and potassium. And a large current could produce heat and light. What's more, these experiments were relatively easy to replicate. So the voltaic pile not only challenged the idea that different forces in nature were not related, it seemed to show the exact opposite. Electricity, chemistry, heat, light all seemed to be very closely related, and many experimenters thought that magnetism had to be involved too. They just couldn't show how. So let's move now to Denmark, to Copenhagen, and to Hans Christian Ørsted. Ørsted grew up in rural Denmark, where he was educated by his parents. What's interesting here is that Ørsted's father ran a pharmacy from their home, and this included a laboratory where the young Hans Christian acted as his assistant and also carried out experiments of his own. At 17, Ørsted passed the entrance exam for the University of Copenhagen. He wanted to study chemistry, but universities at that time taught relatively little science. They were dominated by the faculties of medicine, theology and law. So Ørsted decided to enter the Faculty of Medicine, where he took a degree in pharmacy in 1796. Luckily for Ørsted, a lecturer at the nearby Academy of Surgery, which wasn't part of the university, taught a course in chemical theory, including Lavoisier's new chemistry of elements. After graduating, Ørsted used the Academy's lab and the nearby maternity hospital to write a research dissertation on the origin and function of amniotic fluid. So by the age of 20, Ørsted was an original researcher in chemistry. Now, he couldn't do a doctorate in chemistry because there was no one to supervise it, so instead he wrote a dissertation on the philosophy of science of the great German philosopher Immanuel Kant. Now, according to Kant, our knowledge of nature derives partly from our senses, from observation and experiment. But our understanding of sensory knowledge is imposed by our minds. And what Kant means is that the natural world isn't just out there for us to find, rather we make order using what he calls a priori rules or concepts. In our terms, you could say something like we are hardwired to see the world in a particular way. And Kant says we naturally understand the world as the outcome, the equilibrium of opposing forces of attraction and repulsion. And it follows that matter, in fact the whole universe, is made up of competing polarities, like magnetism, attracting and repelling poles, like electricity, positive and negative charges. And our a priori rules prompt us intuitively to seek unity in nature by tracing the forces we see to deeper underlying unifying forces. We can't know whether these forces really exist. We can't know the things in themselves, as Kant famously put it, but it's a necessary condition of doing science to pursue a deeper unification. Ørsted defended this view in 1799, concluding that there was indeed, quote, a great fundamental unity pervading the whole of nature. Kant's view was developed by other philosophers around this time into what was known as Naturphilosophie, nature philosophy, and was widely believed in the German-speaking world to be an alternative to the Laplacian view. Volta's pile, of course, could be used to support this kind of view, and Ørsted began experimenting with it. In 1801, he showed the pile's strength could be measured by the amount of gas given off at its poles. And thanks to this kind of work, the Danish government funded his travels to meet Europe's leading natural philosophers, and in 1806 it granted him a professorship in Copenhagen. Just get myself out of the way of Ørsted's diagram. Ørsted used the pile to demonstrate the idea that all forces were connected to deeper primordial forces. And he repeatedly speculated that this should include magnetism. Now, he didn't think of an electric current as a flow, but as what he called a conflict of electricities, a violent process of breaking and remaking equilibrium. And this violence generated heat and light. What about magnetism? He knew people had tried to find an attraction or repulsion between magnetic poles and a current-carrying wire, or between magnetic poles and electric poles on a battery. That is a Newton-like attractive or repulsive force. There wasn't one. But in a lecture on the 21st of April, 1820, he thought he saw a magnetic needle move slightly in the vicinity of a current-carrying wire. The effect was tiny, perhaps accidental, but he repeated the experiment in private. With a stronger pile, a thicker wire, and a more sensitive magnetic needle, he reliably reproduced the effect. In July 1820, he claimed an electric conflict in the wire produced a magnetic effect in the surrounding space. In his words, quote, "The fundamental law of electromagnetism is that the magnetical effect of the electric current has a spiral motion around it." On the slide here, you can see Ørsted's diagram of the effect he'd found. Here is the positive and negative poles of the battery. Here is the north and south pole of the magnet. And what he's showing here is that there's not an attraction or repulsion between the magnet and the wire. Rather, this south pole moves in a westerly direction like this, so that the magnet ends up across the wire like this. And the key point here is that the poles aren't attracted or repelled by the wire. Rather, they set themselves perpendicular to it. This is a difficult effect to find because it's three-dimensional, the magnet moving in a plane perpendicular to the current carrying wire. On the left of this slide, you can see the young Ørsted carrying out his experimental lecture demonstration, and on the right here you can see a much older Ørsted doing the same thing. But this time we are focused right here on the key aspect of the experiment, namely that the magnet here sets itself perpendicular to the current carrying wire. Ørsted had found this effect because he was extremely familiar with the apparatus that he was using, but also, of course, because of his deep commitment to the unity of physical forces and to his strong belief that there must be a relationship between electricity and magnetism of a non-Newtonian kind. Now, Ørsted's own research now moved on to something rather different, but across Europe, his effect caused a sensation. This was not a particularly difficult effect to replicate once you knew what you were looking for. But how was it to be interpreted? In Paris, Laplace's followers tried to turn it into a Newton-like force. But in London, the young Michael Faraday did something very different. Born in 1791, Michael Faraday was the son of a blacksmith. He grew up in Marylebone in West London and received only an elementary education. But at the age of 14, his life changed when he was apprenticed to a nearby bookbinder. And you can see the shop on the slide here. Faraday not only bound books, but he read them as well, including elementary introductions to chemistry and the new science of electricity. He was good with his hands, he had access to tools, and so he made himself a voltaic pile from halfpennies, zinc and bits of rag, and became an amateur experimenter. In 1812, the 24-year-old Faraday was given a ticket to lectures in chemical philosophy by Humphrey Davy at the Royal Institution, the RI, in London, which opened its doors in 1799. You can see it here on the slide. The RI was supposed to use chemical research to improve agriculture and to popularise science with public lectures. The lectures had an important moral and political dimension. We're in the wake of the French Revolution, remember, the Napoleonic Wars are raging, and Britain's rulers wanted to show that nature, as revealed by science, supported an Anglican God and not a revolutionary republic, as was claimed in France. The Professor Davy had made himself famous by using the voltaic pile to electrolyse fused salts and produce new chemical elements like sodium and potassium, for example. Faraday took notes at the lectures, he wrote them up and bound them, and he sent them to Davy asking whether he had a job. Davy was so impressed that he took on the young Faraday as his chemical assistant. You can see Faraday on the slide here, and also the book of his write-up of Davy's lectures. So Faraday moved from homemade experiments to assisting one of the finest chemists in the world in one of the premier science institutions which had the best laboratory facilities in Britain. And London at this time was a very different place from Ørsted's Copenhagen. The British Navy had in fact burned Copenhagen to the ground in 1807, destroying the university because of Denmark's French sympathies. London, meanwhile, was fast becoming the world's largest city, the first industrial metropolis, a major centre of Britain's industrial revolution and hub of its global empire. It's wealthy, filled with engineers and instrument makers, and it has a thriving culture of natural philosophy, especially public shows of chemistry and electricity. The RI is at the top end of this, extremely well equipped and funded. Working as Davy's assistant, Faraday was doing his own research, preparing the first carbon-chlorine compound, for example. In 1820, he was commissioned by the Annals of Philosophy to write an account of Ørsted's electromagnetism. And in doing so, he and Davy turned Ørsted's work into their own research. But their way of researching was different, shaped partly by the Royal Institution itself. Here we can see the private laboratory downstairs, a well-equipped, mainly chemical lab. On the right, you can see a small collection of electrostatic instruments which would slowly grow to become the focus of Faraday's research. Upstairs is the lecture theatre, where the work done below was made into an entertainment and education for large audiences. This public understanding of science wasn't just part of Faraday's job, it was part of how he researched. For him, experiment rather than theory was the way to investigate the natural world. Faraday used theory as a heuristic device to make sense of what he was seeing and to take his experiments forward. In fact, he was wary of theory beyond its heuristic value because he thought it could easily lead one to draw false conclusions. So the theories were provisional and adaptable and kept very close to the phenomena. And this was partly because his theory had to be accessible to these big public audiences. That is, he needed to make them see what he'd seen in his private laboratory, make his private conclusions into public knowledge. So let's look at what this meant for electromagnetism. First of all, the RI had the most powerful voltaic pile yet made, and it had a wide range of experimental apparatus and interpretive techniques. So here we can see how Faraday began his researches from these sketches from his notebook. And what he's done here is to hang the current carrying wire vertically rather than horizontally as Ørsted did, and he's dangled the magnetic needle here on a fine thread. And what he's doing in this series of measurements here is moving the needle around and seeing how it turns as the thread is moved around the current carrying wire. Down here, what he's done is to turn this series of temporal measurements into spatial ones. Here you can see the position that the needle takes up as it moves around the wire in the middle here. And then up here, he's drawn this as a series of arrows, and he's beginning to get a sense that this is some kind of rotation around the current carrying wire. So what he's doing is trying to make sense of this strange 3D effect in a way that he can describe to his audiences in lectures, both lay and professional. So Faraday now knows what happens to a magnetic needle in the vicinity of a current-carrying wire. And he now posed the question, what would happen if the magnet were fixed and the wire were free to move? And over here you can see a sketch from his laboratory notebook showing how he tried this. What he's done is to put a kink into the current-carrying wire, here a kind of crank, and then he brings up the north pole of a magnet and he finds that the wire flips around into the magnet. If he brings up a south pole, the wire flips around the other way into the magnet. And he has represented this by putting arrows showing a circulation this way around the north pole and a circulation the other way around a south pole. And Faraday called this magnetic rotations. He thought he'd found the essence of the Ørsted effect, what he called magnetic rotations. And he also reasoned that if you could somehow keep the pole of a magnet in the middle of the crank would rotate endlessly. And he achieved this, and you can see this little sketch down here, by having the magnet fixed in a little bowl here and an electrolyte to carry current. And then he hangs a wire inside, which will now rotate endlessly around the magnet. Over here you can see the demonstration apparatus that he built to show a bigger audience. So on this side you have the magnet rotating endlessly around the wire, and over on this side the wire rotating around the magnet. And this of course is the essence of an electric motor. Now this is a difficult effect to communicate to other people, this three-dimensional effect, and so Faraday made this little apparatus here which he could send to other natural philosophers, and all you had to do was to pour an electrolyte into the bottom and then attach these two ends to a voltaic pile, and you would see this magnetic rotation happening right in front of your eyes. He could communicate this interesting three-dimensional effect to other people. So another technique that Faraday used to investigate the space around a magnet was to cover it with a sheet of paper and then sprinkle on some iron filings. And if you give it a few taps, you find these lovely patterns start to appear in the filings, as you can see on this illustration. Here, for example, is a bar magnet. And the interesting to notice here is that these lines which appear in the iron filings, magnetic curves as Faraday called them, seem to begin always on one pole and travel around in a kind of circle and end at the other. Over here you can see something similar. This is now with the pole of the magnet underneath the paper, and now you can see the magnetic curves coming in, converging on the pole, and they're going out of course the other way to reach the other pole at the other end. This one here Faraday found particularly interesting. Here you have a piece of paper around a current carrying wire. You have to imagine the wire coming down and going through the middle here. And what is particularly interesting about this example is that the lines here, the magnetic curves, don't begin and end on a magnetic pole. Rather, they form these circles, continuous circles around the wire. To Faraday, these patterns suggested that electric and magnetic bodies were surrounded by what he called lines of force that were in some way physically real. Now, Faraday wasn't very clear about what they actually are, but he described them as a progressive polarity between contiguous particles, a directional polar tension in space that constituted a physical medium around the magnetic or electric body. But most important for Faraday was that these lines helped him interpret and extend his experiments. And the piece of work that I'll use to illustrate this is some of his most famous research from the early 1830s, when he found electromagnetic induction. Faraday, like Ørsted, believed in the unity of physical forces, though it's harder to trace the origin of Faraday's belief. The idea of the conversion of physical force from work into heat, for example, was commonplace in the experimental community he entered in the 1810s. And of course the voltaic pile exemplifies the idea of one physical force being turned into another. We also know that Faraday read a number of continental philosophers in English translation, but his way of theorizing was really unique and peculiar to him. Anyway, it was this commitment to the unity of physical forces that led him from the early 1820s to try to find the reverse of the Ørsted effect. That is, if a current-carrying wire can produce magnetism, then somehow magnetism must be able to produce an electric current. And Faraday found this effect in 1831 with his famous iron ring experiment. Now, I'm not going to describe those experiments in any detail because I can use the example that Faraday used to illustrate this technique to make the important points that I want to. Like the Ørsted effect, electromagnetic induction was hard to find because it didn't work the way people expected it to. Unlike rotations, it was a transient effect, one that only occurred when currents changed or magnets were moved, and then it lasted only a fraction of a second. Once Faraday found the effect, he found he could reproduce it by plunging a magnet or a current-carrying coil inside another larger coil. On the top left in this illustration, you can see a small coil carrying a current, and these iron filings here on a piece of paper show you the magnetic effect around the coil. Over here we have a demonstration piece to show electromagnetic induction, and here we have a small coil which has a current flowing through it generated by the voltaic pile over here. Here, attached to the larger coil through these wires, is a galvanometer. And this galvanometer is the Ørsted effect turned by Faraday into an instrument. And if a current flows in these wires, there will be a tiny kick on the magnetic needle here. And the way the experiment works is that you push this coil inside the larger coil and you will get a small kick on the needle. When you pull the coil out again, you will get another kick in the opposite direction. So you couldn't measure this transient effect without this new instrument that Faraday had built using the Ørsted effect. Before this, electric currents were measured by the way a frog's leg kicked, or by electrolysis, or by putting the wires on your tongue and feeling the tingle of the electricity. What's also very important here is how Faraday explained this effect. If we look here at the small coil on the top left, we can see how the iron filings have made this magnetic effect in space visible. Faraday imagined this effect around the small coil here, so that as you pushed it inside, these lines cut through the wire in the coil below. And it's this cutting of the wire by the lines in space which causes the small current to flow. And the more intense the lines, or the faster they move, the bigger the current you'll generate, and the more the little needle in this galvanometer will kick. So the lines of force idea gave Faraday a quantitative as well as a qualitative explanation. And the explanation strengthened the idea that these lines of force are a real physical object existing around magnetic and electric bodies. What's more, this reality became predictive when he speculated that the lines were, as he put it, sluggish. That is, that electromagnetic effects, unlike Newton's gravitation, take time to move from one place to another. In 1845, Faraday made another important discovery. He'd long speculated that light, as a natural force, should be related to the forces of electricity and magnetism. He tried to find the effect with electricity, but in 1845 he tried magnetism. He shone a beam of polarized light through a dense prism, viewed through a polarimeter, and then exposed the prism to a very powerful magnet. The light's plane of polarization rotated slightly, and Faraday was delighted by this extraordinary discovery, and he wrote that it showed all natural forces were tied together and have a common origin. He soon repeated the effects electrically and speculated that light might be a vibratory ray moving through space along lines of electric and magnetic force. So by the late 1840s, Faraday's theory of electromagnetism was quite unlike Newton's theory of gravitation. The effects were three-dimensional, depended upon motion and fluctuating currents, and didn't act instantaneously. They occurred in a physical medium in space and took time to travel, perhaps at the velocity of light. He'd shifted attention from matter, from wires, capacitors and batteries, to the space around them. He'd made electric and magnetic lines of force, fields as he came to call them, the focus of attention. And that attention was soon drawn to a couple of mathematicians, both Scotsmen, who were trying to build mathematical theories of electromagnetism. The most important, of course, was James Clerk Maxwell, and I'll conclude by talking about Maxwell's work. So see you in the next video.